electromotive force and standard electrode potential. First question, given the standard electrode potentials of the following reactions, so we have two reactions, chromium plus 3 plus 3 electrons give chromium metal, and this is the standard electrode potential for this reduction reaction, minus 0.75. And also we have given cadmium and standard electrode potential. Calculate the cell potential for chromium metal plus cadmium to give chromium ion plus cadmium. So the answer, to calculate standard electrode potential, it's equal the standard electrode potential of the half cell where reduction occurs. So reduction always happens at the cathode. Remember, red cat, reduction at cathode, red, reduction cathode, minus the standard electrode potential of the half cell where oxidation occurs. So oxidation always happens at the anode. Remember, anox, anode, oxidation. From the given standard electrode potential values, first deduce in which half cell reduction will occur. The species with the higher standard electrode potential value would be reduced. So remember that. So the higher standard electrode potential, it will be reduced. So chromium standard electrode potential is minus 0.75 volt, while cadmium it's minus 0.404 volt. So due to it is higher or less negative E value, so cadmium will be reduced because this number is higher than this number. Minus 0.4 or negative 0.4 is higher than negative 0.75. So now the standard electrode potential values can be substituted. So we need to substitute in this equation. So cadmium, where reduction will happen, minus the one for chromium, equal minus 0.4 minus negative 0.75 equal 0.35 volt. Next question. From the half equations below, determine the cell reaction and standard cell potential. So this is bromate ion, this is the half equation, first half equation, and this is the standard electrode potential for bromate, 1.44, while for iodine is 0.54. Which is higher? The higher one, of course, is 1.44. So the reduction will happen here, and oxidation for iodine will happen. But iodine cannot be oxidized, so we need to reverse the equation. As in the previous question, using the standard electrode potential values to deduce where reduction and oxidation occur respectively. So we went through this equation before, we need to apply it again. From the given standard electrode potential values, first deduce in which half cell reduction will occur, same like previous question. The species with the higher standard electron potential value will be reduced. So here bromate plus 1.44 volt, while iodine 0.54 volt. So bromate will be reduced. So the half equations are reduction, same, because here gain of electrons. So the reduction will be the same. But as the iodine half cell is where oxidation occurs, its reduction equation would be reversed, must be reversed, and needs to be multiplied by 3, as it only has 2 electrons. but in the half equation the top it's 6 electrons, so iodine equation must be multiplied by 3. So let's see, oxidation 6 iodide give 3 iodine, so we reverse the equation, plus 6 electrons, so now it's oxidation reaction because it's loss of electrons over all equations, so we need to combine them together to give this final equation. And standard electrode potential or cell, the final standard electrode potential equal bromate where reduction happen minus iodine where oxidation happen equal, and don't forget to put the minus, this is from the equation or the law, equal 0.9 volt. Next, from the following data, so we have data here, identify the strongest oxidizing agent and the strongest reducing agent. So if reduction happen, this means it's oxidizing agent. And we said the most favorable one to be reduced with the highest standard electrode potential. So here, this one has the highest standard electrode potential, copper. So it's the most one can be reduced. So it's the strongest oxidizing agent. While, as you can see here, minus or negative 2.37, this is the lowest standard electrode potential. So this is the most one can be oxidized in the 3. So this is the most reducing agent, magnesium, but we need to reverse the equation because magnesium metal is reducing agent. Let's see. So here standard electrode potential of copper and magnesium and zinc. The species with the higher standard electrode potential is the most easily reduced. So copper is the most easily reduced because it has 0.34 higher than this and that. So is the strongest oxidizing agent because it can be reduced, so it's oxidizing agent. The species with the lowest standard electrode potential value is the hardest to be reduced, but it's a reverse reaction. We need to reverse the reaction. We'll have the species that is the most easily oxidized. So magnesium has the lowest standard electrode potential value, therefore magnesium is the species most easily oxidized. So is the strongest reducing agent. Magnesium metal, not magnesium ion. If you say magnesium ion, this is wrong. You have to reverse the equation. Next, using the data for standard electrode potential values in previous equations, predict whether a reaction will be spontaneous between the following pairs. For the reaction to be spontaneous, the cell potential must be higher than 0. If it's less than 0, it's not spontaneous and the reaction will not occur. So we need to see copper and iodine, cadmium and bromate in acidic solution, chromium, metal and magnesium ion. Write equations and calculate the cell potential for the reactions that will occur as written. So when we calculate the cell potential, if it's higher than 0, reaction will happen and it's spontaneous. But if it's less than 0, the reaction will not happen and it's not spontaneous. Let's see. So no reaction can occur as both iodine and copper can only be reduced based on the equations provided. So iodine can be reduced to iodide and the copper ion can be reduced to copper metal. So we cannot react copper ion with iodine. Both are oxidizing agent. Both can be reduced. So cannot be react with each other. With no species present that can be oxidized, a redox equation cannot occur. Next, bromate can be reduced to bromide, while cadmium can be oxidized to cadmium. Cadmium metal can be oxidized to cadmium ion. Half equations, reduction. This is the reduction for bromate. We saw that before. And the cadmium reduction reaction needs to be reversed because reduction here, reduction reaction needs to be reversed to be oxidation reaction. So in that case, 3 cadmium will give 3 cadmium plus 3 cadmium ion. So this oxidation. And we have to add electrons here. So electrons here missed. So 3 times 2, it's 6 plus. So it should be plus 6 electron. Okay. So overall equations, bromate plus 6H plus 3 cadmium give bromide plus 3 water plus 3 cadmium ion. But we didn't add electrons here because we didn't add electrons here also. But they are equal. Here 6 electrons and 6 electrons, so no problem. So the cell potential, this is the equation. So the one standard electrode potential of the one reduced or reduction happen here minus standard electrode potential for the oxidation here. So equal 1.44 minus negative 0.4 equals 0.184 volt. So this is higher than 0, so the reaction is spontaneous and can occur or can happen. So this question, as given in the question, chromium metal would be oxidized to chromium ion, and the magnesium ion would be reduced to magnesium metal. This is the half equation, reduction. It's magnesium gain electrons, magnesium ion gain electrons to give magnesium metal. And in the chromium reduction reaction needs to be reversed. So chromium metal will give chromium ion plus 3 electrons. So here 3 electrons lost and here 2 electrons gained. So we have to multiply the first one by 3 and multiply the second one by 2. So in that case we'll have 6 electrons and 6 electrons, so can be cancelled with each other, and the overall will be 3 magnesium ion plus chromium give magnesium metal plus chromium. When we apply this law or this rule, so where reduction happen? Reduction happen in magnesium. So the standard electrode potential of magnesium is 2.37 volt. And where oxidation happen? Oxidation happen in chromium. And this is the standard electrode potential of chromium. And overall is negative 1.62. So it's less than 0. So the reaction is not spontaneous and will not occur. Next. The standard electrode potential for the reaction aluminum plus chromium ion give aluminum ion plus chromium is 0.92 volt at 298 Kelvin. What is the standard free energy change for this reaction? So this is the equation, half equation, oxidation, aluminum oxidized into aluminum ion plus 3 electron, chromium ion, this is the reduction, plus 3 electron give chromium metal. So the number of electrons the same, so it can be cancelled with each other. The standard free energy change is calculated using this rule or this law. Delta G equal minus N F E, standard electron. N is the number of moles of electrons. F is Faraday constant, and this is standard electrode potential or cell potential. So N here we have 3 mole of electrons. F is constant, and it's a given cell potential equal 0.92 volt for this equation. So multiply them. So negative 3 mole times 96500, this constant, C per mole times 0.92 volt. So mole -1 and the mole will be cancelled with each other. So it's C times V at the end. And this is joule. Remember that. C times V times volt equal joule. And the answer is -2.7 times 10 power 5. So this is joule, divided by 1000 will be in kilojoule, -270 kilojoule.